So for our final learning module of the course, we'll look at how to set up problem 1038 from the final exam. And what we're trying to do is compute the moment of inertia of this blue shaded area about the x-axis. Yours will probably have random values, but it's going to be for specific values of A and B. Here for the version I saw, it was 10 inches in A and 5 inches in B. So if you notice, this is exactly what we did on the last problem. You just need to represent this area as a combination, either a direct addition or subtraction of fundamental shapes. So one way you could do it is take the entire area going up from the origin to A plus B and Y, and then over to 2A and X, and then subtract away these two triangles. Or the way, if you again use solutions that may be available to you as kind of a motivation for your starting point, you'll see that they choose to do a totally additive approach, which is to take and draw a triangle of base width A and height B, and then in addition have another triangle that has height B plus A, and then base A. So it's kind of hard to see, and unless you print it out and draw it, it might not be overly obvious to you. But you got triangle here, you got triangle here, and then you got little, what turns out to be a square here, A by A. So that's exactly what they're showing you here. And I think it's always valuable when you do these to make very, very nice drawings. Because if you make very nice drawings, the math will just be a lot easier for you. So all that you're going to need, going back to slides 15, are these formulas, and you can write them down if you want. The moment of inertia of the rectangle about its centroid axis, and the moment of the inertia of the triangle about its centroid axis. So use those formulas. And if I were you, remember you're going to have to use the parallel axis theorem, because, for example, for this rectangle, the square, just to make it easy, you will compute that using that formula, the moment of inertia about an axis which is 3 inches high. So you're going to have to use the parallel axis theorem and add on 3 squared plus this area in order to adjust to your axes of interest. So this is a nice tabular structure that's good to keep in mind, because this has all the various quantities that we would need. Notice for segment 1, just put in the area, which is just going to be, for the case of the rectangle, 6 times 6, or 36 square inches. dy is just the vertical separation between the axis of interest and the centroid, which is 3 inches. Right? You can compute the moment of inertia about, this is the centroid axis, so just go back to this formula. Notice for a rectangle, it's 1/12 the base times the height cubed. So just 1/12 the base, which is 6, it's a square, so it really doesn't matter, times 6 cubed. Put that number in there. A dy squared, that's just this number times that number squared. And then just add these two columns together. So this is just a nice bookkeeping tool that might be useful for you. If you use this segmentation, note that since each of these is an actual solid, you will just add all of these together. If you use the alternative segmentation that I talked about, where you take big rectangle, triangle, and triangle, make sure that you subtract away the moments of inertia of the triangle. But the procedure works the exact same way as the prior example. So if you're confused and you're like, hey, I thought he was going to do the actual example, go back and watch the video from the prior learning module, and we go over a very similar example in more detail. So that is it. Congrats on making it to the end of the course.